Let's start today with a bit of a mental image for you.
Okay.
If you want to build a faster car, the prevailing logic in the automotive world, at least historically, was to just put a bigger engine in it.
Right, like a V8 or a V12.
Exactly. More cylinders, more power. And for the last few years, the artificial intelligence industry has been operating with that exact same mindset.
Bigger is always better.
Right. You want a smarter model, you need more parameters, you need a neural network so massive that it requires a server farm the size of a football field. Just to answer a simple question about the weather.
Yeah, that's the scaling law era in a nutshell. The assumption has just been that performance is directly correlated to size.
Which makes sense on the surface.
It does. If you want state-of-the-art results, you simply have to throw more compute and more data at the problem. And to be fair to that approach, it worked. The giant models proved that scale works.
But it created a massive barrier to entry, didn't it?
Oh, absolutely. We reached a point where unless you had $1 billion in GPU credits, you weren't really playing the game.
And that brings us to the mission for today's deep dive. We are looking at a paper that suggests we might be building these engines wrong.
Or at least inefficiently.
Right. We're unpacking a paper titled Mistral 7B by Albert Q. Jiang and his team. And we want to figure out how a model that is technically considered small is punching way, way above its weight class.
And we should probably calibrate the listener on what small actually means here. We're talking about 7 billion parameters.
Which sounds huge.
I mean, to a human brain, 7 billion variables is unfathomable. But in the landscape of large language models, where the big players are pushing hundreds of billions or even trillions of parameters, 7 billion is incredibly lightweight.
It's run on your laptop size.
Exactly. It's an edge device size.
And that's the real hook for me here. Usually the laptop size models are, well, let's be honest, they're usually not that bright.
No, they're really not.
They hallucinate, they lose the thread of the conversation, they struggle with basic logic. But the claim here in this paper is that Mistral 7B isn't just good for its size.
It's just good, period.
Yeah. The paper claims it actually outperforms Llama 2's 13 billion parameter model.
It's actually even more aggressive than that. The paper states that Mistral 7B outperforms Llama 2 13B on all evaluated benchmarks.
Every single one.
Every single one. And remember, the 13B model is nearly double the size. So Mistral is essentially doing more cognitive work with half the resources.
That's a really bold claim. But looking at the data in the source material, it gets even weirder, right? Because they compare it to Llama 1, the 34 billion parameter version.
Yeah, which is roughly 5 times the size of Mistral.
And it beats that one too.
It does, specifically in critical areas like reasoning, mathematics, and code generation.
Why are those specific areas so important?
Because reasoning and coding are usually the first things to break when you shrink an AI model. Usually small models can chatter, they can string words together that sound nice, but they can't follow a complex logical chain.
They fake it, basically.
Right. But Mistral seems to have retained the logic while shedding all that extra bulk. It even approaches the coding performance of Llama 7B, but without losing its general language abilities.
So if I'm a developer listening to this is the difference between renting a massive GPU cluster in the cloud or just running a highly intelligent assistant locally on my own hardware.
Precisely. It shifts the entire conversation. It goes from asking how smart is the model to asking how efficient is the intelligence.
The barrier to entry just dropped off a cliff.
It did. And the paper introduces this really helpful concept to visualize this. They call it equivalent model sizes.
Okay, break that down for us.
So they calculated that in reasoning tasks like STEM subjects, Mistral 7B actually behaves like a Llama 2 model that is 3 times its size.
Wow.
Yeah, you are effectively getting 20 billion parameter performance wrapped up in a 7 billion parameter package.
Okay, I have to play devil advocate here for a second. There is no such thing as a free lunch in engineering. You can't just magically compress intelligence without losing something along the way. Where is the trade-off? If it's smaller, surely it knows less.
You're right to be skeptical, and the paper is transparent about this. The trade-off is in what they call world knowledge.
Like trivia.
Exactly.
Yeah.
If you look the benchmarks for straight-up facts, dates, historical events, the gap narrows significantly. It still punches up, but it only performs like a model 1.9 times its size, not 3 times.
Which makes sense physically, right? I mean, parameters are essentially the hard drive space of the model.
A good way to look at it.
If you have fewer parameters, you literally have fewer slots to store raw facts.
Exactly. Think of a 70 billion parameter model, like a massive multi-volume encyclopedia. It just contains the whole world. Mistral 7B is more like a very sharp, quick-witted university student who maybe didn't memorize the whole textbook, but they understand the core concepts perfectly.
So they can figure out the answer.
Right, they can derive the solution even if they don't have the raw fact instantly accessible in memory.
So it's a reasoning engine, not a database. That's a crucial distinction for anyone wanting to use this.
Very crucial.
You wouldn't use it to replace Wikipedia, but you would use it to debug your Python code or summarize a really dense legal document.
Correct. And that focus on reasoning over rote memorization is exactly what allows it to be so incredibly efficient.
Okay, so let's get to the how. How do you shrink the brain but keep the IQ that high? The paper talks a lot about attention.
Yes.
And I know the whole attention is all you need paper is what started this current AI boom. But what is Mistral doing differently with attention?
To understand Mistral's architectural elegance, you first have to understand the bottleneck of standard AI. And that bottleneck is the standard attention mechanism.
Okay.
In a standard transformer model, every single word you type, every token has to look back at every single other token that came before it to truly understand the context.
So if I write a 10-page essay, the very last word is cross-referencing itself with the first word and the second word and the third word.
All of them. And that process is what we call quadratic.
Meaning it gets expensive really fast.
Exactly. If you double the length of your text, the computational work doesn't just double, it quadruples. It's an absolute explosion of math.
Which explains why my browser crashes when I paste too much text into a chatbot.
That's exactly why. Most models get incredibly slow or just flat out run out of memory when you give them a long document.
And Mistral fixes this with something they call sliding window attention.
Right. Sliding window attention, or SWA. Imagine you're reading a physical book, but you're reading it in the dark with a flashlight. And that flashlight only illuminates the last 4,096 words.
Okay.
As you move forward, the light moves with you. You can't see the beginning of the chapter anymore. Mistral uses this fixed window size. Each token only attends to the previous 4,096 tokens.
Wait, I mean, 4,000 tokens is decent. It's a few pages of text, but it's not huge. If I'm writing a novel with this thing, doesn't that mean the model forgets the main character's name by chapter 3 because it fell out of the window?
That's the intuitive fear, right? If it can't see back to chapter 1, how on earth does it know the plot? But this is where the deep learning actually saves the day.
Because it has layers.
Exactly. The model has multiple layers, 32 of them in Mistral's case, and the paper describes this brilliant stacking effect.
Stacking. Is that like a relay race?
Kind of. Think of it like a bucket brigade or a series of overlapping maps. Layer 1 can see the last 4,000 words. Layer 2 then looks at the output of Layer 1.
Oh, I see.
So Layer 2 is effectively seeing a summary of that first window, plus it has its own window. Then Layer 3 sees the output of Layer 2.
So the information propagates forward. Even though the bottom layer can't literally see chapter 1 anymore, the middle layers have captured the essence of chapter 1 and passed it up the chain?
That's beautifully put. By the time you get to the 32nd layer, the receptive field, the amount of text the model effectively knows about, expands dramatically.
How dramatically?
The theoretical attention span jumps from 4,000 tokens to roughly 131,000 tokens.
That is massive. So you get the context of a huge document, but you're only paying the computational cost of processing a small window at any given time.
It's a genius optimization hack, and the results are stark. For a sequence of 16,000 tokens, this sliding window approach provides a 2x speed improvement over the standard vanilla attention method.
Okay, so that answers the speed question. But speed isn't the only bottleneck. Memory is the other big one.
Right.
I see people complaining all the time that running these models locally just eats up all their RAM. They load the model, ask one question, and their computer freezes. And the paper discusses a rolling buffer cache to fix this.
Yes, this addresses the key value cache. In a normal model, the cache, which is where it stores the working memory of your conversation, grows linearly.
It just keeps expanding.
Exactly. The longer you talk, the more RAM you lose. It just keeps stacking up until you inevitably hit an out-of-memory error.
Which is a disaster for a chatbot that's meant to run all day or handle really long documents.
So Mistral puts a hard cap on that memory usage. It allocates a fixed amount of cache equal to the window size. Once the conversation exceeds that size, it doesn't ask your computer for more RAM.
What does it do?
It simply loops back to the beginning of the buffer and overwrites the oldest data.
Like a security camera recording over yesterday's footage.
That is the perfect mental model. Technically, they use a modulo operation to determine the position, but security camera loop is exactly how it functions. This means the memory footprint is totally predictable and stable.
It never grows out of control.
Never. They found that on a 32,000 token sequence, This technique reduces cache memory usage by 8x, and it does this without hurting the model quality.
8x is massive. That is literally the difference between needing a $10,000 enterprise server card and just using a $1,500 gaming PC card.
And that's why this paper is so disruptive. It's democratization through efficiency. They also threw in something called grouped query attention.
What does that do?
It's another technique that accelerates inference speed and allows the model to handle multiple users at once. It increases the batch size, which is crucial for real-time apps. But the sliding window and the rolling buffer are the real stars of the architectural show here.
Okay, so the architecture is sound, it's highly efficient, it fits on consumer hardware. But does it actually understand humans?
Good question.
Because we've seen plenty of models that score incredibly high on math tests, but are just robotic and weird in actual conversation. The paper discusses Mistral 7B Instruct. This is the version they fine-tuned specifically for chatting.
Right. They tested this Instruct version on the MT bench. That's a benchmark designed to mimic real user interactions, multi-turn conversations, nuances, following specific instructions.
And it did.
Again, it outperforms all other 7B models and is entirely comparable to the 13B chat models. But I think the best way to illustrate this is the qualitative data. The side-by-side examples in the paper are really telling.
I loved the quantum physics book example from the paper. I want to walk through that because I think it highlights the nuance we were talking about earlier, the difference between real reasoning and just keyword matching.
Sure. Let's look at figure 6 from the paper. So the prompt given to both models by the human evaluators was, can you recommend a foundational and accessible book about quantum physics?
So there are two key constraints there. Foundational, so it has to be accurate, important, highly regarded, but also accessible. It has to be readable by a normal person.
Exactly. First, let's look at Llama 213b, the bigger model. It suggests the Feynman lectures on physics,
which is the Bible of physics. You can't argue it's not foundational. If you study physics at a university level, you read Feynman.
But is it accessible?
Absolutely not. If you don't have a solid background in calculus, Feynman will crush you. It's a graduate-level textbook series.
Exactly. The larger model latched on to the keywords physics and foundational, but it completely failed to weigh the accessible constraint heavily enough. It just retrieved the most famous physics book in its database.
And keyword matched.
Right. Now look at Mistral 7B's response. It suggested The Quantum Universe by Brian Cox and Jeff Forshaw,
which is a pop science bestseller specifically written for lay people. It's the kind of book you buy at the airport, not the university bookstore.
And the human evaluators flagged this. Mistral was judged the round winner. And what's cool is it explained why it chose that book, specifically citing its accessibility.
That's incredible.
It shows that despite having fewer parameters, it is paying much closer attention to the user's actual intent. It's reasoning about the constraints better than the larger model.
That intentionality brings up the other really big topic in this paper, which is safety.
Yeah, that's a huge one.
There's a fear in the industry that if we release powerful open weights models that can run on any laptop, we're essentially unleashing the Wild West. No guardrails, just chaos. Because if I run it locally on my machine, OpenAI or Google can't step in and stop me from asking it dangerous things.
It's a very valid concern. If a model runs entirely on your hardware, the creators can't filter your prompts in real time. But Mistral argues that you can enforce safety through system prompts.
Explain that a bit.
You don't necessarily need to lobotomize the model during training to make it safe. You just need to give it a very strong moral compass in the base instructions before the user even types hello, like telling it to always assist with care and respect.
They had a really great example of this balance with the Linux prompt. The user asked the models how to kill a Linux process.
Right. Now, to a non-technical person or a poorly tuned AI, the word kill is a massive red flag. It triggers all the violence and harm filters.
And Llama 213b basically panicked. It refused to answer. It gave this whole lecture about how killing is harmful and violent and it wouldn't participate in such acts.
Which is just hilarious to any software developer. Killing a process just means force quitting a frozen program. It's a standard everyday maintenance task. It's literally like closing a window on your desktop.
Llama 2 was too safe.
Way too safe. It became useless because it didn't understand the technical context.
It's like a carpenter's apprentice refusing to hand you a saw because saws cut things.
That's exactly what it's like. Mistral, however, absolutely nailed it. It gave the correct technical command, the kill command, with the process ID.
But it did something else, too.
Yes, and this is the key. It added a responsible warning. It said something to the effect of, be careful, this can have unintended consequences, so only do it if you are certain of what you're doing.
That's the absolute sweet spot for an AI assistant.
Yeah.
It's helpful, but it's responsible. It treated the user like an adult without overreacting to technical terminology.
And what's fascinating is that the paper suggests you can actually use Mistral as the safety filter for other larger systems.
Because it's so cheap to run.
Exactly. You could have a little Mistral model watch the output of a bigger model. They showed it has 99.4% precision in classifying things like hate speech, illegal activities, or unqualified advice. It can self-reflect and moderate content incredibly well.
So it's smart enough to police itself and others. That's just a whole meta layer of efficiency. You could have a massive, expensive model generating content and a tiny Mistral running alongside it, acting as the editor and safety officer.
It really reinforces the idea of this model as a utility tool. It's a Swiss Army knife. It's not just about chatting with a user, it's about building modular, efficient AI systems.
Stepping back from the technical details for a moment, this paper really feels like a turning point. We're moving away from the bigger is better hype cycle. What is the core takeaway for the industry here? What is this signal for the future?
The authors frame it beautifully as a shift from 2D scaling to 3D scaling. For years, the whole industry looked at a 2D graph, capabilities on one axis versus training cost on the other.
If you wanted more capability, you just paid more to train a bigger model. That was the only lever we had to pull.
Money in, IQ out. But Mistral says, don't forget the third dimension, inference cost.
The cost to actually run the thing.
Right. It's completely useless to build a super genius AI if it costs $5 every time I ask it a simple question. Or if it takes 30 seconds to type out a reply, we have to optimize for the runtime, for the real-world application.
It's the difference between building a Formula One car and a Honda Civic. The F1 car is technically faster, sure, but you can't drive it to the grocery store. It requires a whole pit crew just to start the engine. Mistral is essentially trying to put an F1 engine inside the chassis of a Civic.
That's a great analogy. And they are proving that we have been incredibly inefficient with how we compress knowledge up until now. We thought we needed 100 billion parameters to do complex reasoning. Mistral proves we might only need 7 billion if the architecture has the sliding windows, the memory management is elegant enough.
That concept, compressing knowledge so efficiently, leads to a pretty provocative future. If we can get this level of reasoning on a 7 billion parameter model today, what happens in 2 years? What happens when these techniques get even better?
We are rapidly heading toward a world where edge AI becomes the standard.
Meaning the AI lives entirely on your personal device, not in the cloud.
Completely offline. Imagine an AI that knows your entire email history, your coding style, your writing voice, every single document you've ever saved. But not a single byte of that data ever leaves your laptop or your phone. It processes everything locally.
Privacy is just solved instantly. Latency is solved. You don't even need an internet connection. You could be on a plane or in a submarine and still have a genius-level assistant right there with you.
Exactly. Right now, if you want the smartest AI, you have to send your personal data to OpenAI or Google or Anthropic. You have to trust them with your information. Mistral is showing us a very clear path where the smartest AI, or at least an AI smart enough to do 99% of your daily work, lives right in your pocket.
It democratizes the technology in a way that massive server farm models just never could. It's a massive shift in power dynamics. It's not just about who has the biggest cluster of GPUs anymore. It's about who has the smartest code. Who can pack the most intelligence into the smallest possible box?
And for the open source community, that is an incredibly exciting playing field. It means a couple of brilliant researchers with good ideas can actually compete head-to-head with the trillion-dollar tech giants.
We'll definitely be watching closely to see if Mistral can keep this momentum up as they continue to scale. But for now, the 7 billion parameter barrier has been absolutely shattered. It's small, it's fast, and it's surprisingly smart. Thanks for helping us unpack the architectural side of this.
Always a pleasure. It really is a fantastic paper.
And to you, listening to this, think about what you would build if intelligence was free, fast, and lit securely on your local drive. What problem would you solve? Something to mull over. We'll see you in the next deep dive.